The chi-squared distribution looks much more like the F distribution than either the Z or the T. It is not symmetrical. It starts at 0 and all values will be greater than 0. You can't have any negative numbers. As the degrees of freedom increase, it becomes closer to symmetric. It doesn't really achieve that very well, but it's going to be skewed to the right, and the distribution is going to look like this. So with degrees of freedom 2, you've got an impossible up. Basically, it can't actually meet the 0, so it looks more like an inverse function, something like that. And every other one, as we increase the degrees of freedom, it's going to stretch out a little bit. This one resembles normality, at least when degrees of freedom equal 30. As you increase that, it's going to look even flatter, basically. Now, in every case, we're going to deal with a right-tailed distribution, so much like what we did with the F and ANOVA. We're going to only have right-tailed tests when we're dealing with the chi-squared distribution. Now, if we're dealing with just one factor, we're going to do what is known as a goodness of fit test. This is going to deal with categorical data, proportions, things along those lines, anything that can fit into different categories. So we're going to have proposed values for our proportions, and our null will be that those are all correct, and our alternative will be that they're not all correct. We need to see if we have a good fit for our categorical data. Now, how expected counts are going to work, and we're going to have at least 3 categories. K is going to be the number of categories, just like it was for ANOVA. We're going to look at the different probabilities, and they're going to have the subscripts 1, 2, 3, 4, 10, 20, whatever they may be. However many we actually have, we're going to have subscripts for them relating to that specific proportion. Now, we're going to have expected counts. So, if you have a 6-sided die and you roll it 60 times, we expect there to be 10 1s, 10 2s, 10 3s, 10 4s, 10 5s, and 10 6s. So E1 would be 10, E2 would be 10, and so forth. Now, in a case like that, all the E values are going to be the same. We may run tests where they're not all going to be the same. We may expect there to be more of one number than another, depending upon what we're doing, or more in one category than another. So in every case, the E expected count is going to equal n times the proportion that equates to it. Alright, so just like the binomial, the mean was n times p, and we're going to do the same thing here. Now the requirements. We certainly need to have some randomly selected data. The data is going to be frequency counts only. We're going to just tally the number of successes, or tally the number in each category that we're dealing with. Now, we need to have at least an expected value of 5 in each category. You can, in some cases, merge categories to make sure that you get 5 in each. The observed counts don't have to be anything. You can have a bunch of observed counts be 0 or less than 5 or whatever. It's only the expected counts that matter. Now here is our test statistic. So O is going to be for the observed, and E is going to be the expected. So we're going to take each observed value, subtract its corresponding expected value from it, square that value, and then divide by the expected value. We're going to do this in each case for each of the different categories, and then you see our summation sign here, the sigma. We're going to add them all up. Now, the degrees of freedom for the chi-squared distribution is k minus 1. So when we use a chart for that, we're going to look at the degrees of freedom as k minus 1, much like n minus 1 for dealing with the t distribution. But k in this case is the number of categories, not the number of data points. Alright, so in our classical approach, we're going to calculate the critical value. Now there'll be a chart to look this up, Alpha, typically things like 0.01, 0.05, 0.10, that sort of thing, nothing really large. Although the chi-squared chart will have values up to probably 0.95 and 0.99 looking at this area over here. Sometimes you can use chi-squared to do two-tailed analysis or even left-tailed analysis in the goodness of fit test. However, it's always going to be right-tailed, so you don't have to worry about ever dividing alpha in half. And as always, if the p-value is less than alpha, we're going to reject. So if it's greater than alpha, we're going to fail to reject. That's how we're going to deal with the conclusions as far as that goes.